Yeah, so here we have returned. We continue the Ebers-Moll transistor model in the saturation region. And we say that the Ebers-Moll equation are useful for determining the circuit condition when transistor is operating in the saturation region. And in this region, that is in the saturation region, both the base emitter junction and the base collector junction are forward biased. So the current IEN and ICR, that is base emitter and base collector reverse, normal and reverse, are flowing simultaneously. And we assume now that the V base emitter, that is the voltage base emitter and the voltage base collector, both exceed VT, which is approximately equal to 25 millivolts, by a sufficient amount for us to neglect the minus one. Yeah, the minus one values are this. And we said we chose it such that VBE and VBC both exceed VT by a significant amount, so that this would be negligible, the minus one. So what we're going to do, we're going to remove the minus one from the equation, and that will simplify it by choosing VBE and VBC significantly larger than the VT. And so let us proceed with that. Yeah, so we're going to be choosing VBE and voltage base collector to exceed VT in such a way that the minus one factor would be negligible. Then if we divide I collector by the I base, what we'll get is alpha forward diode saturation current IO times E voltage base emitter over VT. And then the one is negligible, so we have a minus I the diode saturation current from the collector, ICO, E, the base collector voltage over VT. And then here again, the minus one factor doesn't count because we choose it in such a way that it is negligible. We go now 1 minus alpha saturation IEO, diode saturation current, E to the V base emitter over VT. And the one again is negligible, so we are just leaving out the minus one, which appears in all these equations, by choosing VBE and VBC in such a way that is much greater than VT, so that the minus one is negligible. That's now 1 minus alpha reverse I collector diode saturation current E to the voltage base collector over VT. Minus one again is and we don't know that the collector, the collector emitter the base emitter minus the base collector. And we see that now, but we can manipulate the equation to yield, after some algebraic manipulation, that IC over IB is equal to H into the BC. Reverse. Over what is collected emitter over VT plus HFE over HFC. Where now HFC equals alpha F 1 minus alpha F and HFC equals alpha reverse to the 1 minus now we define the edge saturation point where IC over IB equals 0.9 HFE. Call that, define the edge saturation point. And we find that VCE at this point, that is the edge saturation point. VCE saturation equals VT log 1 plus HF that's over 1 minus 0.9. That's equal to we say typically 0.9 HFE is much greater than 1 plus HFC. All right, now let's draw a plot of this equation with the IB over IC equals HFE. And in this plot, the characteristics have been normalized by letting the abscissa V collector emitter over VT and the ordinate be IC over IB. So let's draw the plot. And so here we have now here we have 0.5. And number 1 is, let's see, 0.9. And both with the saturation region. Two log T forms the active region. Formula 1.5 kilovolts. H of E. HFC 1 plus rho. I would say no, typically 0.9 HFE 1 plus base 1 plus HFC. So that this simplifies. So V for the 2 Newton sat equals to VT log 9 HF now we see now the normalized characteristic of a transistor. So we said the abscissor was VC over VT. Abscissor or the X coordinate, and the Y coordinate or the ordinate was IC over I. Alright, let's keep the plot and let's take some more notes. Remove this portion here. What we have though is that VCE SAT is approximately equal to log 9 HFE over page FC and for example, if HFE equals 100 and HFC equals 0.01, then VCE equals 285. We plug that into the relation and with the HFE equals 100 and HFC equals 0.01. Then we see that VCE is equal to 285 millivolts. This is the relation here. 2.2 plus log HFE over HFC. Alright, if we consider, and for example, and with HFE equals 100, HFC equals 0.01, then IC over IB will be 9.9. That's with HFE equals 100 and HFC equals 0.01. IC over IB is equal to 9.9. Then using, if we find that VC is approximately equal to 0.18 volts rather than 0.1 volts, which we assume in example. And if we recalculate, we find that IC is approximately equal to 9.8 milliamps. However, if HFE equals 100 and HFC equal 0.1. That's the difference. At one time at HFC equals 0.01. So this is 10 times as much. This is 10 times as less. 10 times as much HFC. Then using the appropriate equation here, we find that VCE, and put that, you have to know that VCE will be equal to 0.12 volts. That is using HFC equals 180, HFE equals 100, and the HFC equals 0.01, 10 times more than what we used when HFC was 0.01. We have know that VC is equal to 0.12 volts. A value which is closer to our assumption of 0.1 volts. I know something was at 0.1 volts and 0.12 is much closer, or is closer to 0.1. And so if you use no VC tends to VT log 1 over alpha F as IC over IC tends to 0. Let's get that mathematically. You just write it, squeeze it in here in this little box here. That VCE tends to VT log 1 over alpha forward as IC over IB tends to 0. And therefore, with alpha R equals 0.01, VCE tends to 0.115 volts. And with alpha R equals 0.1, 10 times as less. VCE tends to 0.057, which is, you could see this one 0.057, this is 0.1. This one is greater, this one is less. So as alpha R 0.01, VC tends to 0.115, which that would be approximately equal to 0.12 if we take that to the second decimal place. And with alpha R equals 0.1, 10 times as much, VC tends to 0.05. Many of the circuits study in consider the transistors to be operating in the active region. If such is the case, when there's no ambiguity, when no ambiguity will arise, we will operate, we will represent alpha F as alpha and assume VCE sat to be approximately equal to 0.2. So we just going to leave out the alpha F here, and we just call it alpha, and assume VCE sat is approximately 0.2 volts. And that is when we are operating in the active region, and when there's no ambiguity, that means all the specifications are made and there's no ambiguity. At that time, we will operate alpha F as alpha and assume VC, that is V collector emitter saturation approximately equal to 0.2.